Testing on YouTube. Testing on YouTube. Testing on YouTube. How's it going, Sid? Testing on X. Testing on X. Still not live on X. Okay. Oh, there we go. Testing on X. Okay, it's live on X. Perfect. All right. Let's take a sip of water and let's get this going. Welcome everybody to another Hoopo stream. We're going to start with a pretty crazy cold open here. So today's stream is called Tattoo Robot, and I'm going to be doing a live demo. Wait up, Sid asking me a question before it begins. I was working on a project for a robot VLM guardrails, basically Llama Guard, but for multimodal robots used for safe, unsafe classification of instructions based on the context. Yeah, you could definitely do that. You could have a secondary vision language model that is taking in the robot input and determining whether it's in a safe or unsafe environment, and then basically it has some e-stop-like tool that it can use, so if it ever gets to a point where it feels like it's a very unsafe situation, it can hit the e-stop. And talking about unsafe situations with robots, here's what we're going to do, guys. I'm going to tattoo myself live with my tattoo robot. So this is the RoboCam. So the RoboCam is an overhead view. This, I don't know why there's a lag on it. Let's see. Come on, RoboCam. There we go. Is this live? Let me move my hand there. There's like a lag. There we go. Okay. All right. So that's there. Let me explain a little bit what's going to happen, and then we'll do it. Happy Friday, Max Malley. So this is what my robot looks like. It's 2 WXAI arms. There's 5 or 6 PoE IP cameras. There's 2 RealSense cameras on the grippers. And I created these custom end effectors that hold tattoo machines. And then there's also this palette that has ink on it. And I'm going to be tattooing this spot on my leg. And the tricky part about tattooing here is that you basically have to get it right in the dermis. You don't want it in the epidermis because it'll fade, and you also don't want it in the hypodermis because it'll do what's called a blowout. So it's a very, very tricky manipulation problem. There is an image on the stream. We can't see the video. Can you see it now? All right. Let me turn on this machine. All right, hopefully this doesn't go as bad as the Oculus live stream yesterday, but we'll see. As you can see, there is a red X on my leg that I'm using to basically calibrate. There's a red laser that I need to basically keep my leg in the same position using that red laser. All right, so now we're going to call the robot, and we're going to tell the robot to start the tattoo. And we're actually going to do it using an MCP server. So as you can see, the robot is composed of multiple different nodes, and then each of the nodes has an MCP server. So basically, I can communicate to all the nodes via these tools. So that's what we're going to do here. We're going to run the robot stroke tool. All right. I'm also going to turn on the needles, and you'll hear like this buzzing. So that's what the needles are doing. One of the batteries ran out of battery one quick. All right. Both batteries are on. All right, guys, we're not fucking around. This is a real tattoo here, so I got to focus. I got myself a little joystick here. This joystick basically controls the distance of the end effector. So there's a very, very tiny margin of error. So I have basically something that allows me to shift along the normal vector to the skin by a tiny, tiny amount. And that means that I am using my own pain as a way to determine whether I'm too deep or not deep enough. All right, here we go. The robot's going to start moving. Let's go. My heart rate is so high right now. All right, guys. I might not be able to talk in a second. Oh, fuck, that hurts. All right, we got our first letter down. Again, I'm basically using my pain as a way to determine whether I'm at the correct depth. I think it might have gone a little bit too deep there. How are you controlling the depth? Through MCP? Yeah, basically through a little Atari controller. This design isn't super complicated, so it should only take 5 minutes. Why not use a sensor next to the tip to calculate the proper distance to keep while drawing? Yeah, you could do that. I also considered like a force puck in between the tattoo needle and the actual robot. You could also have some kind of laser sensor type of situation. There's a lot of different solutions here, but you know, this is just my current implementation. See, right now it's not going deep enough. But this fucking left arm goes so fucking deep. Why two robotic arms? So the idea I had there is that the reason you only tattoo with one arm is because you only have one arm. But then I looked at these like luxury tattoo studios where people will go in and they want to get a whole back piece, but they don't want to go like multiple sessions. So what they do is they basically have multiple artists out tattoo them simultaneously. So basically somebody will go get a back piece and you'll have 4 people with 4 tattoo guns all simultaneously tattooing you. So because I'm using a robot, right, I could have multiple arms going. So in theory, at the limit, you could have like 8 arms simultaneously tattooing you, which means that you would be able to tattoo faster. Right? So basically, while one arm is tattooing, the other arm is dipping into the ink. Ow. All right, guys, almost done here. I think this might be a bit scuffed, but we'll see. Holy shit. Steady, steady. Yep, Mark V. I'm praying the robot arms don't fail. There's like a particular failure case where basically if something happens with the arm, the arm shuts off and it like droops forward, and if it does that, it's basically gonna stab my leg and it's gonna hurt really bad. But this tattoo is very short, so hopefully it does the whole thing. Yeah. Like I've tried to do longer ones, but then whenever you do longer ones, inevitably you run into a don't tattoo artists typically wipe the area in between to see what they're doing? Yeah. 100%. That's one, because they're tattooing with kind of multiple different needles. It's a much longer session, you know, like there's a lot of different stuff going on. For this one, As long as I keep my foot and my leg still, then I don't really need to wipe the area. Oh, there was like a weird snap there. It's also like when it's over the shin bone and the needle goes too deep, it goes into the shin bone, and that's what actually hurts. Like right here, if you go too deep, it's just into the meat of the calf, and it doesn't actually matter. All right, I think that's it. Fuck yeah. Let's do it. All right, that's it, guys. I'm going to turn off the needles now. Then I'm going to put a paper towel over the area. I'm going to put this stuff called green soap on it. And we're going to wipe it. All right, guys. Some of the letters are good. Some of them are kind of trash, but you know, that's what you get for live demos. All right. I'm taking my leg back. All right, guys. That was the demo, and now let's go back to the stream. All right. Let's close out the RoboCam here. Cool. Let's talk about what I just did. So I think the easiest way to do that is I have a visualization MCP server that I can run, and then that will allow us to see a simulation of what just happened. Here, let me quickly log in here. Okay. Kill that. I'm kind of just killing a bunch of things, just making sure that okay. So I'm restarting all the MCP servers. This is the most annoying part of MCP servers with cursor, the fact that I have to like toggle these little green things. So annoying. All right, there we go. Now let's run the stroke viz server. And then we'll alt tab into it. Okay, so you can see it has to think a little bit. Just in terms of this agent workflow with MCP, I've kind of found that there's a huge variety in the ability of different models to use bespoke MCP tools, right? So we already know that a lot of the agentic harnesses that people use, such as codecs, right? Like they're using a bunch of tools, but they're basically fine-tuned for these specific tools. And whenever you have a bunch of your own tools, like I have, right? I have, for example, each of the robot nodes has like usually somewhere over 5 to 10 tools. It becomes very difficult for different models to use it. I find that GPT-5 generally can use tools that it has never seen before correctly, but pretty much all the like smaller and less good models have a very hard time dealing with like 30 tools that they've never seen before, especially for something weird like a tattoo robot, right? It's like they don't have anything in their training data set that's like anywhere remotely similar. So I think that's part of the issue with the tools. That's why It's a little bit sketch sometimes. Okay, so it's starting the stroke visualization. Let's run it. I use Visor for my visualization. Pretty great little Python package. I would highly recommend it. Rerun is another popular kind of visualization tool. But this is the actual design that I got tattooed, and this is an AI generated lettering. So I think this is Flux. So Flux generates this design for me, and then I have software that's actually used for pen plotters. So there's these machines that basically turn an image into a series of strokes, and then I basically execute those strokes on the robot, pre-calculating the inverse kinematics of all of it. So you can see this is the actual design simulation here. So this is like a speed up of what actually happened. You can see that basically they dip into these palettes where the ink is, and then they take turns. So while one's dipping, one's going. And the reason this has a thickness is, again, kind of what I was telling you here, right? Where I've basically found that it's impossible to get the accuracy correct of like getting it just so it sits, just so the needle goes only into the dermis, right? So that's why I use this little Atari joystick. So basically, as soon as the needle goes in, I know what the normal vector to the skin is, and I pre-calculate multiple positions using IK along that normal vector, so that at any point during the stroke, I can instantaneously move this joystick, and it'll pull slightly up or it'll push slightly in, right? So what that means is that it's basically open loop control, but I close the loop, right? So because I'm a human and I can feel my skin, I can kind of tell when it's going too deep, and I can kind of tell when it's not going deep enough. So I'm closing the loop and choosing in that what I call the offset dimension, which index in that offset dimension to go. So I basically calculate like a thickness. I do the entire control problem over a thickness, and then I choose the final solution. Let's go in Aries and Snooks and SHC. All right, so that's pretty much that. Now let's do something with that. So my repo for Tapbot is kind of entirely using Low Robot. So you can actually see here, it actually is recording. So here's the recording. So here's the actual data set. You can see this. Let me actually make this a little bit bigger so you guys can see. And you can see that tattoo consisted of 14 episodes. And here are, for example, the videos from the 2 real senses. There you go. So there's my beautiful, gross looking foot. Here's the actual tattoo needle going in and everything. Next thing we're going to do here is we're going to actually upload it to the internet. So I have a script that does that. Let's actually rename this because it has kind of just like a generic name here. Let's call it Tapbot logo skin real Tapbot logo live. How about that? Then we'll do F2, copy that name. Then we'll do scripts. Upload Hugging Face recording. We're going to give it the name of that. Then we're going to hit enter. And there you go. It uploads pretty fast. And that means that we can now go on this. This is the Hugging Face page. I created a page for the Tapbot. You guys can come here, and if we refresh, there it is. Tapbot Live 2024. So this is just like some log. I think basically the preview takes a second, but for example, we can go to a previous data set here, and you can see this is what it's actually going to look like, right? So you have the observation images for each camera, you have the overhead image, and then you have kind of the actual position of the robot, right? So what can we do with this data set, right? Now we have this data set. What are we going to do with this data set? Well, we can fine-tune a VLA. So that's what we're going to be doing today. We're going to be fine-tuning the latest Pi 0.5, this one here, Pi 0.5, which is probably the best open source VLA right now. They just released this in September 2025, so this is basically brand new version. This is what it actually looks like. So it's a VLA, right? It's a VLM, which is this part right here, and then the Action Expert, which makes it a VLA instead of a VLM. And the Action Expert is basically a little diffusion model, and this is the actual actions that get executed on the robot. So these are the basically joint positions, and then the input is 3 camera images. So you can see here the 3 camera images are the 2 gripper cam images, and then what they call the overhead image. Right? And then also the text. How's it going, Julien? So I don't think this overhead image is as useful in my situation, because whenever you're tattooing, you kind of need this like very close-up shot. So what I actually did is that rather than using the overhead image, I fine-tune with what's called the stroke image. So the stroke image is, for example, this right here, right? So it's an image of the design with the specific stroke that is being executed at that point in time, right? So basically, my fine-tune, what I'm going to try to fine-tune OpenPy 0.5 is to use both of the gripper cam images plus this stroke image. All right. And there's 2 different ways of fine-tuning OpenPy that they offer. There's what they call fine-tuning LoRa, and then fine-tuning full. Okay. So you can see here, obviously fine-tuning LoRa, way less memory, and you can do it on a small GPU like an RTX 4090. And it also works on my 3090, for example. And what you do when you fine-tune using a LoRa is that pretty much most of the parts of this model are actually frozen. So you're not actually pushing gradients into any of the parts of this model. What you're doing instead is you're pushing gradients into these WA and WB matrices, which are the 2 components of a low rank adapter, right? So the rank is simply kind of the dimensionality of this WA and WB. When you multiply them, right, because of the way that matrix multiplies work, you can set that R, and that determines how many weights there are in this WA and WB. But because the dimensionality is determined kind of by this input dimension here, the R actually doesn't change the dimensionality of this WBWA in that dimension, right? So it basically means that if you make this R very, very small, the number of parameters in WA and WB is very, very small, which means that whenever you're pushing gradients, the optimizer state isn't very big at all, right? Because there's not a lot of values there, right? Which is why LoRa fine-tuning can be done on a very small computer or small GPU with not a lot of VRAM. Full fine-tuning is when you actually put all of the weights in the model into your optimizer state. You're pushing gradients into all of those. But of course, when you do that, it's going to require a lot more memory, and you're going to have to use a bigger GPU. So I did do, this is not the one we just did, but for example, here's a design. So this is some video game lore. If you guys know what this is, then we can be friends. But you can see here, this is the actual stroke, and here's the left arm, and here's the right arm, or the right gripper cam, left gripper cam, right? So you can see here, these are LoRa fine-tunes. We can even go to my system. These are LoRa fine-tunes that I did on my 3090, and each of them is actually pretty quick here. You can see that basically in like an hour, you can train these LoRa fine-tunes. But those aren't going to be as cool as the full one, so that's what we're going to be doing today. So we're going to use a online GPU cloud service called Data Crunch. All right, so here's my Data Crunch portal. You can see here they got a nice little UI. And we're going to hit this deploy instance. All right, so we have the choice here, on demand or spot. So spot instances are going to be cheaper, but basically they're kind of unstable, right? So the instance might suddenly go offline. So if you have a long training job, you probably don't want to use spot instances, but if you have some kind of short compute job that isn't super important, right? Maybe you're doing a big hyperparameter sweep with a small version of the model. You know, if the instance dies and a couple of those don't get executed, that's totally fine, right? But for this one, we're going to do on demand. Obviously, you get discounts if you want to reserve for longer periods of time. And you can see here, they offer a bunch of different GPUs. So I'm specifically going to go for an H100, and there's H100s that have 8 GPUs per node, you can see here, and then there's H100s that have 1 GPU per node. So I'm going to basically go to H100 with 1 GPU. And this is not actually real, right? It's probably still an H100 that has 8 in the node, but I'm just getting one subset of that, right? So you can use containers and virtual machines to basically parcel those out. So 1x H100, you can choose fixed pricing, dynamic pricing. I don't know. I'm just going to pick fixed pricing. You can pick the location. I'm going to pick Finland 3 here. And then the operating system. So they have some pre-built operating systems for you, but I already trained on a node here, so I actually already have a little operating system, and this is a very nice little feature that DataCrunch offers you, where basically you can load an existing kind of volume, which I have right here, right? So I'm going to click on that one. I don't need any additional storage. I already have the SSH keys set up. And if you have any special startup script, you could put that there as well, but I don't have any of that. So pretty much everything is clicked now, and then I can hit deploy. But actually, before I do that, I have something for you guys. You see this add coupon right here? I have a coupon for you guys. So DataCrunch has sponsored me, and they have given me this code. Use code HUPO100 for 100 euros of free credits on DataCrunch.io. This is pretty big, guys. 100 euros with an H100 at 199 per hour is like 50 hours of H100s. 50 hours of H100s is more than enough to fine-tune Pi Zero, or it's more than enough to run your little experiments. So go ahead and do it. It's free credits. Just go in there. Hey, you can even just run MNIST training. Sweep over MNIST hyperparameter do whatever you want. But would recommend if you guys want. So we're going to get that started. While that's going, I wanted to show you guys a little bit more about this specific data center. So Fin03, this is the data center that we're going to be running this H100 on. This is a data center located here. So this is what it actually looks like. You can see these big, some kind of like cooling or power type situation going on out here. You can see it's right here in the middle of Helsinki, Finland, right? And just to kind of give you an idea of like the relative size of this, right? So for example, this one here, this is a 1 megawatt training center or data center, but actually it uses, I think, all renewable energy. So that's one of the cool things about DataCrunch is that their data centers are basically powered using renewable energy, which is very different from some of the data centers that you have available here in the US, which are literally powered with gas turbines. So for example, here I have the semi-analysis for Meta and XAI's training clusters. So look at that. At North is a 1 megawatt total power. XAI has a 200 megawatt, and they're building the 1.1 gigawatt. Same thing with Meta here. Meta also building a 1 gigawatt AI training cluster. And you can actually see it's kind of a similar design, right? So like, for example, here in the XAI, you have these like kind of like power cooling truck type looking things. That's the same kind of weird stuff that's going on out here, but data centers, guys. All right, here we go. Copy this SSH, and then we're just gonna SSH into this. Boom. And we're in. Look at that, look at that. All right, we can also always make this big, and I think the most fun part about using GPUs like this, let's close out this. Let's also close out this side panel here, is the good old NVIDIA SMI. Damn, look at that. An H100 with 80 gigs. That just looks so much cooler. Like, look at this. This is the computer I have at my house. This is pitiful. This is a 3090 with 24 gigs compared to a H100 with 80 gigs. You know, I'm literally here right now. I'm here. I'm in this building. I'm in this building on this H100. So yeah, guys, I can't recommend this enough. Like, we just live in a weird point in time where you, as a random person on the internet watching this video, can just put your email in, put in that coupon code, and then you could be sitting here in charge of this H100, and you could do whatever you want. And this GPU is better than any GPU I have in my house. You know, I have a bunch of GPUs in my house, but they're all garbage compared to one of these bad boy H100s. So, all right. So what's the next step here? So we created our data set, our TapBot data set, and now we want to fine tune it. So let's close out of this. First thing we're going to actually have to do is we're going to have to basically convert it. So the actual fine-tuning config, so this is in the Pi0 repo, right? They basically have these configs that determine what the training is going to look like, right? So whenever you're fine-tuning, the best place to start is try to find the closest embodiment, right? So if you have a one-arm robot, try to find a training config where they also fine-tune on a one-arm robot, right? In my case, I have a bimanual setup, right? 2 arms, right? There's 2 arms. They're both WXAI arms. I have the gripper cams, and I'm also using this stroke image as the overhead cam. So the closest one that I found was the Pi0 Aloha, right? So Pi0 Aloha. That's I think the closest to my embodiment. And I actually have a sample data set for the Pi0 Aloha here pulled up. Is this one right here. So they actually use 4 images for this one. So you can see they have the left gripper cam, right gripper cam, and then they have what they call the high cam, which is like this overhead view, and then they have what they call the low cam, which is this like ground view, right? So it's a little bit different from mine. I only have the stroke image and then the left and right, but it's the closest. So that's the one that I used as a starting point. So this Pi0 Aloha Pen Uncap. Right? So here's my training configs for the full TapBot fine-tune and the LoRa one, the low mem, so this I did on my 3090, and then this one was the one we're going to do on the H100. So my action dimensionality is actually less than 32, but I don't think you need to mess with this. I think if you mess with this, then it's more trouble than it's worth, right? Realistically, if your action dimensionality, which is basically the total number of joints in your robot, is smaller than this number 32, you can just use action dim equals 32 and then just ignore the other action dimensions. Okay, so here we have the data set. This is interesting here. So whenever you're doing any kind of deep learning, right, and you're feeding data into a model, you want to normalize that data, right? So you don't want your data to have very, very big values, very, very small values. You want your training distribution to be kind of centered on 0 with a roughly nice little Gaussian shape right on the origin, right? So specific arms and specific types of tasks are going to have some bias in the joint space, right? There's going to be some part of the joint space that is much more common than other parts of the joint space. So you want to basically normalize that before you do that. So fortunately, OpenPy has these normalizations for this truss and arm. This isn't perfect. Ideally, I would recalculate this myself for specifically the TapBot, but I think for now it's probably okay. How's it going, little KM? Oh shit. Okay, you guys have some questions here. Hernando, how's it going? If you covered this earlier, but are you doing this purely against paper? As in not accounting much for the elasticity of the surface? Yeah, I do. I have end effectors that do it on paper. So for example, this one here, this is paper. So I have like here, I can show you guys. I have a tattoo needle that is actually a ballpoint pen. I don't know if you guys can see that, but that end effector is actually a pen. So I have data sets where I'm basically using TapBot, but it's basically drawing with a ballpoint pen. And then I have data sets like this. This is the needle that I just used that are actual needles. So that's that. Okay. All right, so we created our config. We also tell it to start from some checkpoints. So in this case, we're going to start from the base Pi05. We also give it a number of training steps and a save interval. All right, so now let's go back to our machine here, right? And actually, let's SSH into it from here as well, just so we can run the NVIDIA SMI and we can see it, because I think that's always fun to look at. Okay, so let's go do our good old watch-n0.1 NVIDIA SMI. There we go. Let's make this a little bit bigger just so it fits. So as soon as we start training, we'll be able to see this bump up in the VRAM usage. So because I already have this container set up, I don't really need to install a bunch of dependencies, but I do need to set some environment variables. So for example, I'm going to tell it which WANB project, my WANB entity, and also these memory allocation settings, right? So this basically prevents this situation with JAX where it like pre-allocates a bunch of memory. And because I'm running agents, not like an agent like but a WANB agent, which is basically a automated process that runs training scripts. And this is how you do hyperparameter sweeping. The agents sometimes don't interact well with the memory, so I just find that these settings help. Command WANB not found. I think we need to cd openpi and then source.vm bin activate. So now we're inside we're in Finland. We're here somewhere in this building. We're inside that building. We're inside our little H100. Let's create this sweep. Actually, first of all, let's remove the WANB folder. This contains all the logs. There's probably a bunch of stale crap in there I don't want. So I'm going to create the sweep from a sweep config, which is basically, here's various different hyperparameters that I'm sweeping. And then I'm going to just simply run this agent. So I'm going to copy that command. I'm going to run that agent. All right, you can see it's going to start the WANB agent. And we should see this memory here start blasting upwards. So you can see here, here's the first command that it's running. It's taking a second here. How are people doing? Oh, there we go. Look at that. 553 allocated a little bit. You should see that start going up. All right, because I saved this volume, it should already have the model downloaded. There we go. It's finding the model, so it's loading the model from the cache. So you should see this suddenly go up. There you go, 12. So you see now it loaded the model. Boom, loaded the optimizer. So you can see here the all the different intermediate things that you need to keep track of, like the momentum and all that type of crap, right? And now, boom, there you go. It's about 50 gigs. So not necessarily utilizing all of the memory of this H100, but it's a really small data set anyway, so maybe we could have tuned the batch size a little bit more. There's also another parameter that matters a lot here, which is the this here, the action horizon. So the action horizon is basically... see if there's a nicer picture to show you what that is. But it's kind of like how far back in time are you looking, or how many actions are you predicting when you're doing that chunk, right? So it's basically like your sliding window in time that you're using for this robot, right? And the reason this matters is because if you make this, the bigger you make this, the more memory it's going to take, right? So it's kind of like, for example, image size, where if you make image size big, it just blows up your memory. So the smaller you can make that, the less memory it consumes, but then kind of the shittier the performance. So action horizon is kind of the same. It's like if you make this too small, the model's just going to be kind of pretty shitty because it's on the window in time that it's operating in is kind of very small. But if you make it too big, then you're going to need a pretty big machine to train it. Okay. So there we go. It's training. Look at that. It's going ahead. It's not a lot of steps. So just for this video, I didn't want to do like a huge amount of steps. If I actually look at some of these other configs, so for example, Pi Zero Fast Full Droid Fine Tune, you can see they're training this for 100,000 steps, which is a lot. You know, that's quite intense. They say it takes 2 days on 8x H100s. I don't have that kind of time for this stream, so I'm doing something much less. I'm doing 4,200 steps on a single H100 with a small action horizon. So I feel like we should be able to finish this by the end of the stream. Okay. Let's see. We talked about LoRa versus not LoRa. We talked about data crunch. We talked about coupon code, which you should definitely use. Like, it's free credits, guys. Just literally log in, go into this node, you know, like run a random model just cuz, and then there you go. Yeah. Okay. We talked about the relatives, these data centers, you know, just the difference here is kind of mind-boggling. It's like you don't realize how much 1 gigawatt is, right? 200 megawatts to 1.1 gigawatts when you realize that this building is 1 megawatt. So like, it's like already the XAI cluster is 200 times this size, and they're about to build one that is 1.1 gigawatts. So it's like mind-boggling amounts of compute and power going into these American data centers. Okay, so coming back here, this is the OpenPi full H100, and these projects are public, so you can go ahead and I think I put the links in the description. So here in the description, you can get the links to these Wannabe projects, so you can look at these training curves. So we got a couple different things here. We have loss, and here's a little tip, right? You see how this loss kind of just, it looks kind of difficult to see, like what you see, it kind of feels like it's flattening out, like what's going on there? So what's actually going on there is that this plot is not actually correct. So you actually want to do this. So here in this, click on this, and then you see this little thing right here. This will basically change it to a log scale. So what we want is a log scale on the y-axis. So let's actually do that. And now it looks a lot better, right? So now you can see, this is kind of what I want to see, right? I want to see this loss go down. This is a little bit easier to see. So then you hit apply. And now this is kind of more useful. Gradient norm is also kind of useful. This basically tells you how big are these steps, right? I think we've lost landscape viz. Yeah, we've visualized this a million times, but I just love this visualization, so I'll wait to pull it up. Explore. It's loading. 100 euros is 75 croissants in my country currency. Those are kind of cheap croissants. I think the 1 euro croissants are probably kind of trash and gross. But all right, let's see. Let's drop a point here. Come on. Can I? How do I drop a point? I forget how to drop a point. Let's see. What about this? Click anywhere. There we go. Boom, there we go. There's our gradient descent. Okay, so the magnitude of this, and this is here, you can jack it up, right? Those steps are basically this gradient norm here, right? So you don't want to be taking huge steps, because whenever you take huge steps, what's happening is that this delta W is very big, right? So basically all the steps, these weights are changing a lot. And as soon as these weights change a lot, then you're kind of catastrophically forgetting what was on this model before, right? So whenever you're fine-tuning this Pi Zero, the physical intelligence team, they spent a lot of time and energy and money to basically create a nice, big, fancy data set that they pushed into this, right? And there's also the pre-training that's been done on the internet. So if you have too much gradients going in, right? You're changing the weights too much, then your model's going to kind of forget about the previous training, which is not good. So you really just want to, fine tuning is almost the art of like figuring out the the tiniest little adjustment you need in order to make it work for your specific embodiment. Okay, so this is the actual run that's going on right now. So we can actually click on this. Let's go down here to the system. Power usage, GPU memory allocated 80%. That's kind of what we expect. And then we have GPU utilization here. So this is another one that you generally want to check. You can see here 100, that's pretty good. There's a big drop right here. Maybe we can investigate that and what's going on with that big drop in GPU utilization. Where's the coupon button? Right here. Oh, the coupon button is whenever you create an instance, it's right here. So right before you deploy, you can add the coupon, and that's where you get the free money. Okay. So while that's training, here's a little tip that I think is kind of cool. So whenever you do a hyperparameter sweep like this, right, something that you can do now, which is actually kind of mind-blowing, is you can go into this chart here, which is basically just the tabular version of all of these plots. And then you see this little download button. You download that as a CSV. So you export that as a CSV. Boom. Now you have this giant table with all that information. And then what you can actually do is you can give any browser-based frontier model that information. So for example, here is GPT-5, and then here's Grok. And I basically just gave it this CSV file, and I also gave it a markdown. So if you're doing any kind of model training or hyperparameter sweeping, you should keep a markdown file that is kind of like your experiment log, right? So in this markdown file, I'll put all the information. So I'll say like, this is what I'm doing. I'm fine-tuning this model. This is the data set that I'm using. Here's information about my specific action dim, action horizon, the different cameras that are on there, right? I'm training this on this specific GPU. This is the commands that I'm using to run this. So I'm basically putting all the information, all the context that someone might need to understand what this experiment is here in this markdown file, so that I can then take that markdown file and the CSV export of my hyperparameter sweep, and I could just ask Grok. I can say, help me understand the results of my sweep over various lower fine-tunes of pi 0.5 on my tapbot embodiment. Attached are a markdown with more details about the fine-tuning and a CSV file containing the results from each run in the sweep. And actually, I found these to be pretty good, you know? So like, it used to be the case that like, you had to have experience and knowledge and almost like a taste to really understand what's going on here, and like, hey, if I change this hyperparameter, what should I be expecting? You know, so there's a lot of like nuance there, and being good at that is really what made the difference between like a good ML engineer and kind of just like an average ML engineer. But the crazy thing is that much like programming is kind of all about managing agents now, there's kind of a similar effect in experiments like this, where you don't really want to be coming to conclusions entirely by yourself. You want to rely on these models because they have very, very good intuition about hyperparameters and models and fine-tuning. They know all of it, right? They know what a LoRa is. They know what the rank size is. So you can see, for example, at the end here, he's like, oh, here's the specific run that I think did best, and here's other things that you could try. So just a little hot tip, but I think it's something that's kind of improved my workflow. And something that I thought was interesting is, for example, Grok just kind of seemingly has the CSV in plain text format in the context, right? It doesn't seem like it did anything special, but GPT-5 Pro actually created a bunch of Python. So look at this. You can see it loaded this CSV file into some kind of mount, and then it actually created a bunch of Python code to scrape it and right? Like, look at this. It's making all these little Python files to basically like parse this CSV. And then after it's done that, then it gives you its opinion. I don't know if this is better or worse, but I thought it was interesting. So you can see here, for example, here's a loss histogram. And at this point, it's already gotten rid of that, but like, that's fucking crazy, you know? Here's it's like, oh, you should move this to that. What's happening here? You constrained the good corner of the space. I don't know, pretty cool stuff. All right, let's see how our training run is doing. Let's come here. We can hover over this. We see it's about 1,000 steps in, so it's about right here. All right. We come back here. You can see it's about 33% done. It's going to take a little bit longer to go. And you can see here the GPU memory on the H100 is about 70 gigs right now out of 80. Okay, what else can I do to buy some time? Oh yeah, this right here. So unfortunately, I kind of got fucked here a little bit, and this is how. So all of the training scripts and the recording that I do, right? So whenever I record that data set, the dataset conversion script, the fine-tuning script, all of those scripts were written using a slightly older Robot dataset format. So in what seemingly is kind of an unlucky timing here, on September 16th, it was just earlier this week, basically once I already finished doing all this stuff, they released a new dataset format, what they're calling Robot Dataset v3.0. So actually a bunch of these scripts are broken. So what I'm showing you here is actually me fine-tuning on a slightly older data set, not the one that we just recorded. And this is kind of standard, right? So whenever you're working on the bleeding edge of technology, like we're doing here with robotics, the tools change rapidly under you, right? So people who worked with TensorFlow might remember this, right? TensorFlow going from 1 to 2, like all the tools change very rapidly if you're on the bleeding edge. So you have to be willing to basically throw all your code away and then rewrite it or modify it. It seems like the biggest change that they did is this streaming. So they call this streaming the robot dataset. And why is this important? So the reason this is important is that, as they say here, to support datasets with potentially millions of episodes resulting in hundreds and millions of individual frames, we merge data from different episodes into the same high-level structure. Okay. So the reason they did this is, like, for example, on our situation, we are fine-tuning on a very small data set that I collected, right? So this Tapbot logo live stream, like if you look at, for example, one of these videos here, this is a 30 megabyte video. So that's pretty much nothing, right? So that means that whenever we're in our H100, we just download this data set at the beginning, and then it's just sitting inside the volume on that actual instance, right? So like the data set is just right there, right next to the GPU on the same exact machine, right? Maybe not the same exact machine. Maybe some of that is being abstracted away by data crunch, but it's basically co-located with the compute, right? But robotics is moving on, and we're starting to get to the point where people using the robot format are starting to train on much bigger data sets. And at some point, you kind of hit the limit of what's practical, and you don't really want to have to download the entire data set on the machine that you're actually doing the compute. So you want to be kind of streaming in that data, right? So the data is existing somewhere else, and then you stream it in as you need it, right? So that seems to be the main thing. And they have some conversions here, but these conversions are always kind of a mess, to be honest, because, I don't know, you're better off just basically re-recording things. That's my potentially unpopular opinion. Okay. Let's go back here. Still going. Let's do this. So we're gonna run one of the fine tunes on this. So we're gonna keep this going, but right here, this is how we're gonna run a fine tune, right? So I pretend I went and I downloaded that. So once that model is done training, it's going to create a checkpoint, and then we're going to have to take that checkpoint from Finland, where it is right now on this machine, and we're going to have to download it locally onto our machine. So I already did that. It's a little bit slow, but you can see here, I just rsync this checkpoint from Finland into my house here in Texas, and then once it's in my house here in Texas, now we can basically run this fine-tuned policy, right? And the way that you do this is actually by splitting it. So the machine that is controlling the robot is actually not the same as the machine that's going to be performing the inference on the actual policy, right? So Hog, this machine here, this is the machine that's actually running the model, or running the robot. This is the machine that's connected to the RealSense cameras. This is the machine that is connected to the robot arms. And then this machine here, this is the 3090. This is the machine that's actually going to run the policy server, which is basically just the model is loaded onto the VRAM, and then it's just sitting there and it just waits. So for example, if I hit enter here, it'll load into the 3090, and we can open up a new thing here to see it. So we can say watch-n 0.1 NVIDIA SMI. There it is, right? So my 24 gigabytes of VRAM on my 3090, about 19 gigabytes of that are now filled up hosting this model. And you can see this model is now, or this policy server is now listening on this port here. So it's basically just sitting there waiting for someone to give it command. So now I'm going to run this tapbot infer script, which we can look at it real quick. Where is it? Examples tapbots in here. Examples tapbot infer right here. So you can see all this is really doing is it's basically creating a robot object, or robot object. You know, it's kind of like a singleton kind of pattern. It reads in the cameras from the left and the right. Here's the basically while loop. And then all it does is it gets the images, converts them into the format that you need to feed it into the model. So you can see here it's a prep image, this thing right here. Convert to U8 letterbox crop, and then resize to the right size. Then it feeds it into the model right here, client.infer. So that's going to basically package it, send it to the policy server. The policy server is going to do the inference. You're going to get back the actual actions. You're going to create this action chunk, and then you're going to execute that action chunk. That's where this send action comes from. Okay, and then you're going to run it. So, for example, let's actually do that right now on the robot. Let's see. Server rejected web connection. Let's see. I think what's happening is yeah, it was waiting for this wrong server. So let's do this. I think this script here is a little bit incorrect. The policy server script, serve policy.py, scripts.serve policy, this one right here. I think we need to give it this exact IP right here. 192.168.1.51. Let's see if that works. Okay, so look at our GPU, again, popped up, so we know it's loaded. Okay. I can hear it. And there you go. Now our port is listening on the right thing. Now let's run it again. Oh no. Rejected again. All right. Where is the coupon button again? Okay, I'm just looking to make sure I'm not missing anything. I can try to debug this live, but it's going to be difficult. I don't have the option to say, back to you, Zuck. Okay, actually, I think I see what's wrong. So I think the port number is wrong. So we go back to infer. Let's actually do this. So we're going to vim. Then we're going to search for 8,000. There it is. Ooh. Okay. Insert. We're going to change this to 3. All right, now let's run it. There we go. So now this is the robot running the fine-tune policy. Let me actually open the RoboCam so you guys can see. It's still, this IP camera, like the cache is really weird. And that's it. Here, wait up. RoboCam, come on, RoboCam. Come on, RoboCam, you're our only hope. Oh, there it is. So this is the actual model. And you can see that it basically, like, it kind of overfits. That's the problem that I'm running into, is that, like, when I fine tune it on one of these tapbot scripts, I either don't push enough gradients, right? Like, don't overwrite it enough, make it catastrophically forget all the stuff, and then it just kind of like, it's not accurate. It's kind of like too loose with its motions, or I kind of overfit it, and then it just kind of only does tapbot stuff. So it's very difficult to create a fine tune that simultaneously does tapbot correctly and also takes actions that are kind of not tapbot specific. So for example, if I gave it a prompt here, so this is what the prompts for tapbot look like, right? When I'm fine tuning, I'm giving it what the prompt is, and the prompt might be something like ink dip right arm and ink dip left right large to fill, and then left arm at rest. So this basically telling it dip this arm in this and draw this specific stroke, and I'm giving it a stroke image, right? So I'm giving it something that looks like this. I showed it before, but something that looks like this. Right, so I'm conditioning it on this image. So rather than conditioning it on, for example, this image, which is what physical intelligence conditions it on, right, the actual overhead image, I kind of thought that this overhead image might just like not be good enough, because it's like the stuff you're looking at is so tiny with these tattoos that it's like kind of impossible. So let's do this. Let's get wave your left arm up and down. Let's see if it can run that prompt, see what happens. All right, so now it's trying to do wave your left arm up and down. And it kind of does it. You see, it still very much wants to dip this right arm into the ink. But you can see that left arm is going up and down. So that's a little bit of that generalization is still in there, you see? And that's the tricky part about robots right now, is that these models are very small. Whenever you fine tune them, you kind of overfit them a little bit. So finding that right balance is very difficult. Okay, let's close out this RoboCam. You can see this constantly drops RealSense frames. Those RealSense cameras are kind of low-key trash. I say this as someone who uses RealSense cameras all the time. I probably have like 10 different RealSense cameras in this room right now, and I've been using them for easily like a decade at this point, but they're just not good. You know, they take a lot of power, so they constantly fail, right? Not fail, like fail at the USB port level. You know what I'm saying? Like you basically have to unplug, replug them, which is a huge pain. But unfortunately, we kind of still have to use them because they're really the only good depth camera that you can buy at a consumer price point. I think long term we don't use the depth anyways, so we just have RGB cameras, and then once we have RGB cameras, then webcams are quite good. All right, so we fine-tuned it, or we recorded the data set, we uploaded it to Hugging Face, we spun up our H100, we downloaded the model and the data set to the H100, we fine-tuned on that H100, we downloaded the checkpoint from the H100 to our local computer, and then on our local computer, we ran the policy server on our 3090, and then on our robot computer, which is the one connected to all the devices, we ran this infer script. Okay, so that's basically the full pipeline, guys. That's like everything you need to do. I would tell you to look at my scripts, but unfortunately my scripts are using the old LaRobot dataset format. So actually I kind of have to rewrite everything for this new LaRobot dataset format, probably do something a little bit different. Anytime you have to rewrite things, it's a good opportunity to potentially refactor. But one more thing I wanted to maybe look at is this paper. So let's take a break here. All right. So this is a paper that's a little kind of made the rounds in social media. It's called Dream Control, Human-Inspired Whole Body Manipulation, Human Control for Scene Interaction via Guided Diffusion. And what this model does is it's basically, we've seen this before. So there was a paper that we read called Real to Sim to Real. This is basically that, right? Where you're starting with mocap trajectories of humans. So basically you have a large data set of mocap animations, which is basically a human that wore one of those mocap suits and then basically just performed various different things, like pick up a quarter off the ground, like throw a baseball, shovel or something like that. And they're just basically performing all these actions. You create this data set of these human trajectories. So you're taking real data from real humans, and then you're moving it into the digital space where it's now a sequence of motions on a human skeleton, right? That human skeleton, now you need to do what's called retargeting into a robot skeleton, right? So the robot has a slightly different kinematic tree. It has slightly different joints, but you can retarget an animation so that the animation of the human using a shovel can be turned into a rough animation of the robot using a shovel, right? It's not going to be perfect, but it's a starting point. Once you have that starting point, then you can use reinforcement learning to actually refine these, right? So you're going from real to sim, right? So now you just do your standard reinforcement learning. You have some complicated reward function. Here's your actual reward function that they use. For example, penalizing deviation from joint angles, penalizing high torques and accelerations, penalizing high action rate changes, penalizing foot sliding while in ground contact, right? So the reason you can do this, the reason people do this is because in simulation, you know this, right? So why don't you do reinforcement learning in the real world? Because in the real world, I don't really know what the position of my humanoid's foot is relative to the ground, right? It's not a very, I don't really have a way to get that information in a very accurate way. But in a simulator, I know exactly where the foot is, and I know exactly where the ground is, so I can give you an extremely granular reward penalty for how much the foot is sliding. So RL in simulation, where you have all these oracle states that make it very easy to have these complicated reward functions and that are very rich and allow you a very dense signal, which you can use to get gradients and push it into your policy. And then once you have that policy that has been trained in simulation, you can start adding domain randomization, making it more robust, increasing the variance or the kind of the spread of your simulation so that it encompasses a very large variety of different visual things, large variety of different frictions, large variety of slightly different torques that are possible, and all this different control parameters for the robot. And then once you do that, then you deploy back to the real world, and ideally zero shot, but if you can't zero shot it, you can always kind of fine tune on a little bit of the real data. So you're going real to sim to real, right? So even though people are talking about this paper like it's some brand new shit, it's like people have had this idea before. It's just now starting to become the go-to idea. And I think this is a big change in what's happening in robotics, because if you think about what the idea of for example, TapBot, the current stack that I have for TapBot, or the current stack that people use for something like Pi0, the core idea of this was like, okay, we're going to have humans that basically teleoperate this robot. That's going to give us a data set, and then we're going to basically do supervised learning on this teleop data set, and hopefully the robot works, right? So hopefully if you basically do imitation learning starting from a VLM, that should be enough to get you a general purpose robot. And we're kind of realizing that it's not quite there. That's not quite good enough to get the level of quality that we want. So now everybody's pivoting and they're all moving to this new strategy, right? So here is the new strategy is basically this real to sim to real, or a variant of that, right? So now you have people using a VR headset, performing actions, right? And what you're getting there is not robot teleop data, what you're getting is this kind of like human data, right? You're basically getting these kind of egocentric human trajectories of just like, hey, this is me opening a drawer, right? But with this type of data, you can get this type of, you can basically use a pose tracker to get the position of the hands, right? And once you have the position of the hands, you can retarget that to the humanoid hands. Then you can use that as the starting point for simulation and reinforcement learning, and then you just deploy from that zero-shot sim to real. And that seems to be what Figure is doing, right? That seems to be what other people are doing. So I think we're at the end of the imitation learning era, and we're now entering this kind of like egocentric real to sim to real era. And here's another reason why I think this is going to be huge. Another reason why this is going to be huge is because of this. So yesterday, Meta announced their, I don't know if they're Ray-Ban or Oculus. I don't know which one, what they're calling this one, but it's basically egocentric cameras, right? So think about a world where everyone is wearing these glasses. In a world where everyone is wearing these glasses, the size of this type of data set is going to like 1000x easily, right? So like that when people do record these data sets, you know, maybe they can record like 1,000 episodes, 100,000 episodes, right? Imagine a world where you have like the entire human race is wearing these glasses. Now you're going to have like billions of these data sets doing every possible thing that you could ever imagine. And I think that is how we're going to get general purpose robots, right? So, I don't know. I just thought this was important because I think we're in a very important transition in robotics, right? When I first thought about TapBot, my idea was that I was basically going to do the simulation learning stack, right? So the simulation learning stack would have been, hey, I'm going to teleoperate this tattoo robot. I'm going to collect a bunch of episodes of me teleoperating this tattoo robot. Then I'm going to fine tune a open source foundation model, which is effectively just like a little layer on top of a VLM, right? And then that's going to be good enough to do the tattoos. And the answer is it's not. It's not good enough to do the tattoos. What do I think is actually going to work? Probably something like this. Imagine if I got the top 100 tattoo artists to wear these type of glasses and then just do a bunch of tattooing, right? Look at this guy. This guy's got a tattoo. Nice. Now, all of a sudden, I have a much richer data set, and I could do a strategy kind of like this, right? Where I take those thousands of tattoo artists wearing Ray-Ban Meta glasses, I basically track the positions of their hands, I use that to retarget to basically the TapBot end effector, and then I use reinforcement learning to fix that in sim, and then I basically just deploy it in real. So, I don't know, I just kind of wanted to bring that up. How are you tunneling your local host for your policy model to your training run? So whenever you spin up a machine like this, right, the NeoCloud company, in this case DataCrunch, will basically give you the option to say, hey, what SSH key do you want to give this machine? And you give it the SSH key of your local machine. So what that means is that I can just copy this, right? And then I can just SSH directly into it. So you can see here it actually finished. So it started the next run, right? So we were doing a sweep, so it finished that sweep, it saved the thing, and then and now it's running the next one. But yeah, so that's how I'm capable of doing that, right? So I can SSH here, into that machine, and as soon as I hit this button, I'm now in Finland. Which is, I think that's like the coolest part about the cloud, right? Like sometimes people like take it for granted, but like right here in this little terminal, I'm in Austin, Texas. But as soon as I hit this SSH root, boom, now I'm in Finland. Now I'm in this building. I'm offended you're doing everything as root. This isn't even a real machine. This is some virtual machine, probably wrapped inside another virtual machine, wrapped inside another virtual machine. So if you mean tunneling port, you can do it in VS Code or with SSH directly. Yeah, so you can do it entirely via the terminal, but you can also, like, for example, right here, this isn't even the machine that I'm running. This is a Windows machine that I use for streaming, but this machine right here, right, this is not the same machine. This OOP machine is actually a different machine in my house, and this entire window here, so this file system right here, that's actually on that machine. So you can SSH directly into it via the terminal, but you can also SSH into it via your IDE. And that allows you to look at the file system, potentially look at images. So like, for example, what I did right there, where I just like click on this image and it opens it, you can't do that via the SSH on the terminal. You'd have to basically forward the front. It's kind of annoying to do, versus if you SSH via your IDE, you can do this type of stuff like this. But generally for like an H100 that I'm renting in the cloud, I don't need to open up an image, right? I don't need to see anything. The only thing I need to do is like basically clone my repo and then hit train, and then it just goes into trains, and then I can visualize the actual output here in WANB. Don't let the machine hear you say that. The machines are always listening. They always know. You got to be nice to them. Okay. I think that's pretty much anything. I don't really have anything else I wanted to say. Do you guys have any more questions? If not, I was going to stop this and start looking at my leg, see if I'm bleeding or not. Let me see. It's not too bad. It's a little sketch. Definitely didn't do it perfect, but it's pretty good. I don't know if you guys can see this. Can you see that? Maybe not. It's all right. I have a bunch of other shitty tattoos. Also, here's another interesting thing. That means I now have 4 robot tattoos. And I think with 4 robot tattoos, I am probably the most tattooed human from a robot in all of human history. Which is pretty crazy. I don't think any other human being has ever gotten more robotic tattoos than I have. So maybe I should reach out to the Guinness World Record people. But I don't know if they give a shit about that particular record. But I don't know. I thought that was kind of cool. All right, that's pretty much it, guys. I'm still going to continue to work on this tattoo robot project. It's kind of like a filler project a little bit. If you do, so there is a repo. All the code is open source. You can go and check it out. And I do have this here. I have a wait list. So I have a Google form set up. If you have any interest in potentially receiving a robot tattoo, definitely fill that out. And if I get a certain amount of interest, right, if I get a bunch of people that sign up and I start to have a bunch of people that are interested in potentially receiving this, I'll probably put more effort into this project. I might even try to raise some money for it, maybe get some VC to raise some money. But yeah, if nobody signs up for this wait list, I'm probably not going to spend too much more time on this. But yeah, check it out. Open source tattoo robot. Cool. I think, let me check if there's anything else I wanted to mention. We talked about LoRa versus full fine tuning. We talked about LaRobot. You see, I'm already behind. So whenever you see this, whenever you make a fork, as soon as you see this one commit, 5 commits behind, these guys move fast. The Hugging Face LaRobot team, like every single day I come in here, I refresh this page, they already did a bunch of pushes. So these guys are pushing hard. And you can see here, if you see this button here, which says open pull request, that means you can't automatically pull, which means that there's a merge conflict, which means that some of the changes that I made are now fucked, and they're fucked because of this 3.0. So that's kind of what I mean, is that this demo is already outdated. I need to go and pull this and figure out what they changed that was slightly different. Data Crunch, great. Neo Cloud, this is now my go-to cloud option machine. I do have a code which is in the description. You should go ahead, get your 100 free credits, spin up an H100, do something cool. It always feels great to use a huge GPU in the cloud. In this case, you're using a GPU in this ominous dark building in Finland that is powered by renewable energy, so you can feel good about it. And then you can marvel at the size of these training clusters that Meta and xAI are building. We had our WANB. You can use these models to basically tell you what type of experiments to run. They actually have pretty good intuition. And yeah, we kind of ended it with this as well. So I just thought that this was in the news, and I think it's important, and I think we're starting to see a transition in robotics from kind of like an imitation learning teleoperation paradigm into now this kind of like real to sim to real kind of like big egocentric data sets, especially as we move into a future where you have a lot of people wearing these, right? And this might be how UBI works, right? So UBI in the future might be that you wear this all day, and then you create this type of data set, and then robotics companies pay you for that, right? So UBI might not be, hey, the government just gives you money just because you're part of a nation state. And instead, it's the way that UBI works is that corporations give you money to get the data that is coming from your glasses, right? So all you have to do is sit there and like do your bed in the morning and like do your dishwasher, and then some humanoid robotics company is going to pay you for that data. And in my case, right, if I wanted to do a tattoo robot, maybe I would buy a bunch of these glasses, right? If some VC gave me money, if a bunch of you guys signed up for this on the wait list, what I might do is I might use that money to get a bunch of these glasses and then go to a bunch of tattoo shops here in Austin and then get them to wear those glasses and get them to just tattoo for a day wearing these glasses, and then take that data set and then basically do this strategy. That's, I think, the best strategy right now. Much better than what I was kind of doing, which is kind of like imitation learning strategy, which is just kind of not super good because it's just you're never going to get the diversity that you're going to be able to get from here. But that's pretty much it, guys. Hope that was entertaining. Hope you have a good weekend. I think a lot of factories are already doing that in Shenzhen. Yeah, it's already become like we're already past the imitation learning paradigm. We're already in this new paradigm. People just haven't like caught on fast enough yet. But all right, thanks everybody for listening. Thank you, Julien, Jigar, Hernando Vidal, Max, Molly, Lil KM, SHZ, Snooks, Mark B, Sid. Thanks everybody for listening. Hope you had a great time and have a great weekend.